Hello. In this video, we're going to cover some of the main points within the first part of Chapter 8, which deals with nonlinear optimization problems. So, first of all, as we've been working in the linear world up to now, the linear world is characterized by the kinds of expressions on the left side of this. So, for example, when we first set up our linear programs, we would use the sum product function within Excel, and all sum product is doing is multiplying a data value times one of the changing cells or the variables. So I've kind of colored them here in terms of the D values. The D cells correspond to data values, which again those are the ones that you typically color in light blue just to organize your model. And it's basically data that's given with the problem. The C cells are the changing cells, which you typically color in yellow, and those are the ones that you're asking the solver model to come back and recommend the optimal solution for. So, for example, on the left side here on the linear formulas, the first one, sum product, we've been using that a lot. So, for example, we would say the sum product of the cost or the profit per unit times the number of units the model decides to produce, for example, which is, again, that's a pure sort of algebraic representation, and in each case it's just simply a data value times a changing variable. Same thing goes with the ones below that. So you can do whatever kind of operations you want on the data. Like in this case, you've got a couple of data cells added together divided by a third data cell. But at the end of the day, that comes to one essentially recalculated data value is what that really does. And you're multiplying that one data value times one changing cell, which is C4 in this case. You also have some logic, which is based. The logic now is based on the data, which says if D2 is greater than or equal to that, then choose this linear expression 2 times C3, and if the data value is less than 2, then you would choose the other, again, linear expression, which is 3 times C4. So again, you can have like logic functions as long as they're on the date. They involve the criteria involves only the data values and not the changing cells or the variables. Same thing with a sum if. Again, the key thing about all of these, straight sum of data values, you can do whatever you want. Down here is just a bunch of, again, linear operations. 2 times C1 variable plus 3 times C4 variable plus the C6 variable. So all of these, again, are forms of linear expressions. The ones on the right now are the ones that if you've, I'm sure during the course you've bumped into some situations where you try to run a solver model and it says, it's not adhering to the requirements of a linear model. And what typically was happening is you had one of these things going on. And so here are the classic ones. Like this top one is whenever you have, and this is carried throughout, whenever you have a variable multiplied times another variable, that's definitely in the camp of nonlinearity. So like this top one, the sum product where both sides are variables, that's definitely nonlinear. Here you've got, in the second one, you've got the addition of two variables, which is no problem, but you're dividing that by a third variable, which is a problem. So again, if you've got variables multiplied times each other or divided by each other, that's a real problem, and that puts us into that nonlinear camp. Here's a logic statement: if C2 is greater than this. Well, the problem and why this differs is that the criteria is depending on a variable cell. In other words, if C2, which again is a changing cell, it's a variable, and that's different from the one on the left, which was if D2, where D2 is just simply a known data value it doesn't change within your model and it's known. So this next one also, again, sum if you're asking it to sum based on the results of values in the variable cells, that's going to throw you into the nonlinear world. all these round, max, min, absolute value. Again, any of these functions on a variable cell, a changing cell, those will cause you problems. And again, down at the bottom is just, again, more examples of anytime you have a variable multiplied times another, or in the very last one, in the case of a variable multiplied times itself, where it's C1 squared in this case. So again, anytime you've got a model, and in this chapter we focus really on objectives that include potentially some of these nonlinear expressions. Now, we're not worrying too much about nonlinearities in the constraints, because for most problems dealing with nonlinearity that you'll deal with, they all occur in the objective function. So, if you think back, for example, in the Jones and Soda, the cost of ginseng was nonlinear in the amount that was demanded, and the amount demanded was nonlinear in the price of the soda. So they all made themselves. They all entered the problem in terms of the objective. So anyway, so again, the nonlinear programming is used to model what we call non-proportional relationships, and that's different than a proportional relationship. A proportional relationship, whereas for every door you sell, you get $300 in profit. So if you sell one, you get 300. If you sell two, you get 600. If you sell three, you get 900. That's a proportional relationship. It's not like you get $300 for the first door you sell, then you get only $200 for the second door you sell, and then you get only $100 for the third door you sell. That would be a non-proportional relationship. So proportional relationships follow that. They're kind of handled with sort of the simple algebra, which is typically a variable times a coefficient or a constant, but nonlinear formulas are how you would use to measure these non-proportional relationships. And again, it's much more difficult as you step into the world of nonlinearity, both in terms of formulating the models and kind of converting the given data into sort of a model format, but also even it's much more difficult to solve those problems once you get them set up. And those were just some key points made in the chapter. So again, this notion of proportionality is where the objective function again is proportional to some level of activity. A non-proportional relationship is when it's not proportional to the level of activity. So like if you double the level of activity, then how that contributes to the objective, if it's not linear, if it's not proportional, then you're in the world of nonlinearity. So, like for example, in the Windor problem, we had over on the left, we had the potential production rate for the doors. We could make anywhere from 0 to 4 or 5 doors per week. And you'll notice, remember, you made $300 in profit for each one. So the first one generated 300, the second one generated 600, etc. Or the second one totaled 600, etc. Hold on just a second. Okay, so that's a purely proportional relationship. You had a different rate, simply the amount of profit. The rates were different. For doors it was $300. For windows it was $500. But nevertheless, they were following those proportional relationships. So non-proportional relationships would be ones. There's kind of a key distinction. Is the one on the left is this notion of a decreasing marginal return. So that would be the example that said like, oh, okay, if for the first window we sell, we get 500. For the second window we sell, we get 400. We get 300 for the third window we sell. We get 200 for the next window, etc. In other words, and that's sort of a characteristic if you're trying to sort of sell too much into a market. The way to do that, you maybe have to reduce your price the more you sell into a market. So that would be an example of a decreasing marginal return. And on the left, you've got a nice smooth representation of that. But on the right, you've got what's called a piecewise linear, which says, if you're in this low value level of activity, it follows one particular rate, straight line, but then it changes to a different rate as the level of activity increases. And then the third rate actually is even lower, and that's what kicks in after you get to a certain level of activity, a higher level of activity. And again, this would be a case where you're trying to maximize profit, and but the more you produce, the more likely you are to have to incur overtime. So that would mean the more you chose to produce, the more expensive your labor costs would get, which would decrease your marginal return. So that's an example of how that would play out in this case. The one on the left here is another example of decreasing marginal returns. It's just, in this case, you've got what's called discontinuities. And that is, there's no smooth transition. It's like once you get to this level of activity, if you produce one tiny bit more, then you incur this like jump up to the next level. And these functions are really kind of problematic in a nonlinear model. The ones on the previous page that were smooth are sort of readily solvable typically, but one where they have these discontinuities can be really problematic. But hopefully, they're not that common though. But it happens like if you're ordering, the cost of something you're buying from somebody. For example, if they have volume discounts that kick in at a certain level, that's what creates those discontinuities. It's like if you order with Amazon, and you get, you're ordering something that costs $1 each, and you order 34 of them. Well, if you order 34 of them at $1 each, it'll cost you $34 plus shipping. But if you order the 35th one, it's only going to cost you $35 because it's going to be, $35 for the item you're buying, and you don't have to pay shipping. So it literally goes from 34 plus shipping, which might be, say, $5. So it goes from 39 if you order 34 of them down to 35 if you buy one more. Those kind of things cause all kind of problems for these types of models. Now the other is increasing marginal returns. That means you would get higher profit the more you sell, which tends not to be the case, but the optimization models have a lot of problem with those types of curve shapes. So just giving you a heads up in terms of the types that are easy to solve in nonlinear solver and the ones that are difficult. So it also talks about like how do we even know what our nonlinear formula is. So the easy way to do that, and you can do this in JMP easily, which you had in Stat 201, but you can also do it in Excel. And it goes something like this. And let me shell out to Excel here, and I'll show you. So we've got this data here, and we've got a level of activity, and we've got an associated profit with it. And we go, wow, look, if you do 2 items or whatever, you get a profit of $16 each. Or I'm sorry, $16 total. That kind of implies you've got, you're getting $8 per profit for each of those 2 that you're choosing here. And that's cool. So looks like we're making like $8 in profit for each activity. But then we go up from 2 to 4, and our profit only goes up by $8 more. So now this kind of says, that's interesting, because that would imply we did 4, we're only getting $6 in profit for each. So what's happening is your first couple are very profitable at $8 each. Your next 2, they're only profitable at about $4 each. And then you add one more, it's still at $4 each. And then you're adding two more, and it's only going up by $2. So those are only being profitable like at $1 each or something. So you go, wow, that's definitely not proportional. The profit is not proportional to the level of activity. So here's what you would do. First of all, you can graph it, and I encourage you to always do this because there's nothing better than simply looking at the data in terms of the shape of the relationship. So the best one to do is do a scatter plot on this XY chart. So I'm just going to do an XY scatter plot, and I've got my values here on the graph. And so, you know what? What I can do then in Excel is I can add a trend line to it. And all I do is I'm just going to right-click on the series and say Add Trend Line. Now, when it does that, in this, depending on which version of Excel you're using, it'll pop some type of a window that allows you to choose that. Now, it fit this, by default, it goes to a linear trend line. It fit this linear trend line on there. And you have the options to display the equation on the chart down here in the lower right. So check it out. So this is the equation that it fit in there. That means that the profit, Y, the y-axis, is equal to 2 times the level of activity plus 15. And so another thing that of course I always like to add as well is this notion of the R-squared value, which if you recall from Stat 201 is an expression in terms of what percent of the variation is attributed to the given relationship that you're showing. And when I put that on there, we get, all right, we've got a trend line now and the R-squared value. So what this says is that 86% of the variation of the reason they're different in terms of profit is due to the level of activity, is what that implies. But you can look at that and you go, that's really not the best fit perhaps. So what I'm going to do is actually remove that particular trend line, and I'm going to ask it, I'm going to say, let's try it again. Let's add a trend line. But this time, let me do a polynomial of order 2, which, if you recall, a polynomial of order 2 is like a parabola. And so that's actually kind of a better looking fit. And I can display the equation on the chart, which is right here. And I can also do one more thing, and that is I'm going to display the R-squared value as well. Now, what's kind of cool is that now, let me put those over here, you've got now a, you've got R-squared that went from 86% explanation of the variation to now a tighter fit, which has 98 or 99% of the variation explained by this relationship as characterized by this polynomial of order 2, meaning it's x squared is its highest ordered term. So this is the way you can start to explore taking data and characterizing the nonlinear function associated with it. So like earlier in the semester when we were looking at Jones and soda, and we said, wow, the amount of demand is a function of the price we set for the soda. And we said that the lower the price, the higher the price would be, or I'm sorry, the lower the price, the higher the demand would be. And as we move the price up, it becomes more of a high-end boutique drink, and the amount of demand would decrease. And again, if you recall, that had sort of nonlinearity aspects to it as well. So anyway, let's get back to the slides here. So again, this is how we construct this, construct a nonlinear formula. So let's talk about one very important characteristic related to nonlinear programming models, and that's the following. Suppose we have this, there's only one changing cell, it's x, but we've got this very nonlinear profit function. It's, it involves x to the 5th, x to the 4th, x to the 3rd, x squared, and x. Then we've only got two constraints. One is that basically the value of x must be between 0 and 5. So it's greater than or equal to 0, less than or equal to 5. Very simple model. we could pop it right into a little solver model. And that's what we're going to do right here. So here we are. We've got the little model. We've got profit, which if you look up here in the formula bar is that long complicated expression. There's x to the fifth right there. There's the x to the fourth, etc. So we got the expression for profit, and we've got our constraint that says, the value of x must take on a value less than or equal to 5. So we go to solver and we're going to solve this. So we choose solver and we say maximize profit by changing x, which is the named range of the changing cell, and that x is less than or equal to the maximum, which is the named range corresponding to this cell E5, which is the value 5. So we're going to use GRG nonlinear now because we've moved out of the world of linear programming models, and we're going to solve it. And boom, we solved it. So we had a starting value of 0 in our changing cell, and it gave an optimal solution of x being equal to 0.371, which maximized our profit at $3.19. That sounds great. But let me show you another thing. Suppose we, I'll just go to this model. Suppose we, instead of starting with 0, we just happen to randomly put in the value of 3, and then let's solve it again. So again, we just have just a different number that happens to be sitting in the changing cell, and we solve that. Guess what? The optimal solution is no longer 0.3 something. It's now 3.126, and it gives a much higher value for profit. And you're thinking, like, what the heck? I wasn't paying attention to what number I had in the changing cell. If I start this at 5, by the way, and again rerun solver, then we rerun solver, then it in fact gives a value of 5 in this case. It says, oh, we can't do any better than that. So again, we started at 0. When we ran solver, came out to 1 value. When we started with a different value of 3, it came out with a different optimal solution and a different objective. And we started with, if we started at, say, 4.7, I started at 5 earlier, I'll start at 4.7. It comes up, it might be run on some of the other models, but it can come up with an even different number, like coming up with a value equal to 5. Not sure why that may not be coming to the same solution as the book, but that's okay. The point of this is the following. That x to the fifth, x to the fourth, well, the pink line here is basically that function graphed out. So the x value is ranging from 0 to 5, and the y-axis is the given value of profit under these various possible values of x. Now, the 3 values that we would come to here basically represent what we call local minimums. And the way these nonlinear programming solvers work is, like for the first case, we started with an x value equal to 0, and what it does is it says which is the direction to improve, and it goes, well, take a step in this direction and you'll improve. And it keeps improving, it gets to this point, and then it says, well, don't take any more steps to the right because it starts to get worse. And then it says, well, I must be at the top of a mountain is what it thinks. But in fact, it's only at the top of a small hill. When we started it at a value of 3, then it goes to the top here. I mean, it does the same thing. It starts at 3, goes up a bit, hits 3.7, and then it says, I'm at the top of a hill, and it says, okay, we're good to go there. So for these kind of complicated nonlinear problems, and this one is not well behaved. This is, this would be a real problem having a, x to the fifth kind of function in your model. It calls out the danger of solving nonlinear problems, and that is you have to be really careful where you are having it start the search from. And it starts the search from whatever value you sort of put in that yellow cell as a starting spot. So sometimes if, it's just kind of good practice if you are dealing with a nonlinear problem, start out with your changing cells all set to 0 and run the model. Then set them to some sort of other extreme value and see what happens in that case. So for example, like if we were back at this example here, and again, I'm not sure why. Let me just do it on this one. So if we started with 10 here, we just happened to leave 10 in the cell, and we ran solver, then it's still saying 0 is the best. So, but anyway, the point is try some extreme values in there for the yellow changing cells, rerun solver a few times, so that you'll be sort of assured that indeed it is the optimal solution, sort of a global optimal. Now, the other thing that we want to cover here is again, we're revisiting that Windor Glass Company. And this was the basic model that we had before. We had, unit profit for doors, unit profit for windows. We had the hourly consumptions for the different types of products at the 3 different plants. Now, our total profit was a sum product of the units produced times the unit profit. So it was a purely linear model in that respect. So what's changed now is that they go, well, you know what, we forgot that there may be some marketing costs if we literally start producing these things and try to sell them. And it basically says that you can sell some without any real advertising at all. But if you want to try to sell a whole bunch of them, then you're going to have to do a lot more advertising. And so the curve fitting was used to come up with these estimates in terms of the marketing costs as a function of the number of doors you produce and the number of windows you produce. And those are given right here in the middle. The marketing cost for doors is $25 times the number of doors you produce squared. And for marketing costs for windows, it's basically 2/3 of $100 times the number of windows that you produce squared. So if you consider the marketing costs now against the original profit values that we were given, then it says, okay, we've got now profit as a function of the profit of per unit of the door minus the marketing costs in each case. And so, this fourth bullet point is basically pointing out that this is now the sort of the full algebraic expression of the objective function. And again, if you notice, it's got a d squared, which means a variable times itself, and you've got a w squared, which is a variable times itself. So we're now immediately into this world of nonlinearity. So the profit graphs, by the way, are shown here, and that is, although the one on the left looks pretty darn linear, it's really not. It's the production rate for doors, and it doesn't decrease as dramatically as the one on the right. In other words, 25 times the number of doors squared versus 66 times the number of windows squared. So, and also you've got the ability to make a lot more windows, so it's kind of over a larger range. So this may look fairly linear also up to the point of reaching 4, but then those heavy marketing costs really start to cut into your profit, and your actual profit would then start to drop. So again, that's just in isolation each of these sort of profit functions for doors and the profit function for windows that now take into consideration the marketing costs. So we've got And let me go back to here. So now we've got again unit profit values that are different than our original problem. But we also have these marketing costs. And let me show you what that looks like in the model here. So I'm going to go back out to Excel. And here's our model. So you'll notice right now if I produce no doors or no windows, then I end up getting no gross profit from selling doors and windows, nor do I incur any costs for marketing because I'm not choosing to sell either product at all. But look what happens if I decide to sell one door. I decide to make and sell one door per week. Well, guess what? We're going to make one door, the marketing cost, which is, again, the number of doors produced squared times $25. So it's going to be 1 squared times $25, which is $25. So our gross profit on the sales, which is the sum product in terms of the changing cells times the objective function, or the profit per unit values up here. But now we are subtracting off the marketing costs, which is just simply the sum of all of these values here. And that's how we're getting. So if we make just one door, our profit for the week will be $350. And if we make 2 doors, then check it out. Well, 2 squared is 4. 4 times $25 is 100. So now we're incurring $100. So if we produce 2 doors, our profit now drops down to, or our profit now goes to 650. Now again, watch this very carefully. As we make one door, our profit is $350. As we make 2, it's $650, which means that second door really only added $300. The first door gave us a profit of $350. The second door only added $300 of profit. And guess what? The third door goes from, again, in this case, $650 up to $900. Again, as we go from 2 to 3. So that one, that one only added $250 as we went from $650 up to $900. So again, you've got this decreasing marginal profit is what's going on. So nevertheless, we've got the model set up. Same kind of relationship would happen for Windows as well. First one is, $633. The second one would be $500 basically, as we go from $633 up to $1133. So again, it too is exhibiting that decreasing marginal profit. So we set this up. We go to Solver. We're using the nonlinear again. We just say we can't violate the hours at the factories, and we solve it, and it comes out to these values here. So we've got, in this case, 3.2 doors and 4.2 windows to be produced every week. And then we could sort of experiment in terms of, well, if we round those both down, what would happen? Round one down, one up, etc. So anyway, that's basically the implementation of this in the WinDoor problem. And the point to make on this is that this red region is the feasible region of that's where all the points within the red region are obeying the factory hour constraints. But what's happening now is, instead of having like an objective function that's a straight line, remember we used to kind of move that ruler up in the direction of improvement? Well, now it's a curved shape. So you can imagine you've got like an arc, or an arc that you're now moving out in the direction of improvement. And another very distinctive characteristic, by the way, is before, when we were in the linear world, and this is just kind of a sidebar, but in the linear world, the optimal solutions were always at what we call the corner points of the feasible region. They would be either at 0, 6, at whatever value this is, 2, 6, 4, 3, or 4, 0. So in the linear world, we were guaranteed to have a solution at one of the corner points. That's not the case with nonlinear. they actually can be optimized at a point not only on the sort of a line segment between corner points, but sometimes we'll see the optimal solution actually will even lie in the interior of the feasible region. So it requires a different sort of set of algorithms to try to find that point. Now, the last example we want to cover in this video is this notion of the portfolio selection. And again, optimization is used pretty widely in the world of finance. And one of the key ways that it's used is to basically, like in this case, identify a portfolio that for some level of desired return, it will decide your investments to achieve that return, but do so at minimal risk. And risk is measured by the potential variation or standard deviation in return. So you finance majors probably are pretty handy with this, but I'm just going to kind of walk through this to give you a flavor for this type of an application. So again, there's two things we're concerned about. One is expected return and the other is risk. And the conventional wisdom, of course, in finance and investing is that the only way you get a higher return is if you're willing to incur higher risk. But that's you can then at that point, if you know that relationship between risk and return, then you can find the level of risk you're comfortable with and pursue a maximal return related to that. So this particular optimization model is basically, again, it's kind of a version of a cost-benefit trade-off problem where, again, in this case, you're trying to minimize risk, but you want it to deliver a certain expected return. So you're putting a minimal acceptable level of return, and you are going to be asking it to give you the division of the assets such that you minimize that risk. So this problem is simple. We've got three different stocks. They're very different in terms of their expected return as well as their amount of risk. So what we're looking for is a portfolio that will deliver an 18% expected return, but do so with minimal risk. So there's three stocks. So again, check it out. The first two have an expected return that's pretty high. So these might be, high beta stocks in the NASDAQ or small cap world. Whereas the third stock has an expected return of 8%, and that's something like, a stodgy Fortune 100 company in the consumer goods business. So we not only have the expected return categorized for each stock, but we also have a risk or standard deviation, which is, as you can see, for the first two, they are very risky. Their standard deviation, meaning from year to year, how much the expected return could jump around, varies considerably. Now, you'll notice that risk, the standard deviation, if that was a value of 0, that would imply that investment would deliver the expected return without question every year. It would never be higher and it would never be lower. When that standard deviation is high, that means the one, stock number one, sometimes it has it'll return 50%, and the next year it may lose 20%. I mean, it's very different than something that has a very small amount of variation. So each security or investment has a measure of standard deviation associated with it. But we also characterize the following, and that is, over on the right here, we look at the covariance, which is the joint risk per stock. And that means between stocks 1 and 2, the fact that it's a positive covariance suggests that they tend to both move up at the same time. 1 and 3, on the other hand, those tend to sort of go in different directions. If one is up, the other one tends to be going down. The same thing between 2 and 3. So these joint risks are measures of, again, the relationship between any pair of these three securities, and it measures not only whether they tend to move upward together or whether they move apart, but also the degree of which they tend to stick together and the degree of which they tend to go apart. So the algebraic formulation is, and I'll just kind of highlight this a bit. The risk is measured by, it's basically the you add the variances of all the components of variation. And so the first three expressions in the objective function basically are those are the variances associated with the individual securities 1, 2, and 3. And so what it says is the more you, S1 is the amount of your portfolio you're going to put in investment 1. And what it says is the more the more you put in there, then that's going to be the amount of variance in terms of your overall portfolio as delivered by the investment that you have in security 1. So the first three terms are just straight up measures of variance, again, that are a function of the standard deviation of the securities as well as the amount of your portfolio you're putting in there. The last three expressions are all those covariance ones. And basically in this case it's the amount, like for this expression here, it's the amount you put into S, the proportion that you put into S times the proportion that you put into, or S1, the proportion you put into S2, times its covariance of 0.04, that was the value on the previous page between 1 and 2, and you multiply it times 2 since there's 2 stocks involved in that. So these last three expressions, they all have the value of 2 times the covariance times the proportions that you put in each of the pairs of securities. The other constraints are that, again, this is basically the weighted return for your portfolio, which is going to be the portion of your portfolio you put in security 1 times 21% times the amount you put in 2 times its return, expected return, which is 30%, times security 3 proportion times its expected return of 8%. And you've got to make sure that that weighted return for your portfolio is greater than or equal to 18%. Finally, the proportions must add up to 100%, and they can't take on negative values. So that's the algebraic expression. So here we are in terms of the model. So we'll go back here, portfolio selection. So we've got our expected returns here, that's data. We've got our standard deviations of risk, that's here, that's data. And then we've got our little covariations right here, depending on the combinations of stock 1 and 2, stock 2 and 3, and stock 1 and 3. So our portfolio is, these are the changing cells, so we're trying to come up with something that totals 100%. So like we could say, wow, let's do 100%, let's put all of our money in stock number 1. Well, if we do that, wow, that we're going to get a return of 21%. Remember, we said that's the return for investment in stock 1. You get 21% on the money you put into stock 1. We put all 100% of our money in it. Our portfolio will have an expected return of 21%. The risk, on the other hand, is as follows. It's going to be basically this. It's going to be the standard deviation. It's going to be your standard deviation. Let me go to the formula here. Squared times the proportion, which is 100%, plus the covariances. But since stock 2 and stock 3 have no investments in them, all those expressions are going to be 0, because again it's the stock 1 proportion times stock 2 proportion, which is 0. Stock 1 times stock 3 is 0, and stock 2 times stock 3 is 0. So none of these covariances are going to kick in at this point. So again, this is just simply 0.25 squared is now the representation for the variance of this particular portfolio where you're putting all of your money into stock number 1. And when we then take the square root of the variance to equal the standard deviation, we just simply have it reported down here as standard deviation. So that's the model. So let's see what it does here. So we're going to set it up to solve it. We're using the nonlinear solver. We're trying to minimize variance by changing the yellow changing cells, which are range named portfolio. We want them to total 100%. So that's that simple expression right there. And we also want our expected return to be greater than or equal to the minimum expected return. So the expected return is that weighted average. It's really kind of a sum product of the portfolio changing cells times the expected returns. And we solve it. Oops. And it's solving the prior model. Hold on just a second. Let me close this one. Let me close it. Say don't save. Let me try it again. So yes, y'all are seeing firsthand the dangers of. And here we go. So we've indeed solved it. It's got the percent of the portfolios. They total 100%. It delivers exactly an expected return of 18%, but it has a risk of standard deviation of 15%, which, if you notice, of course, is somewhere between. We'll just highlight these. The standard deviation of your portfolio now is somewhere between going all in on stock 3, which is your minimal risk of standard deviation of 5%, versus the stock 2, which has a risk of 45% in terms of the standard deviation. So as you would expect, it's this sort of middle ground. It achieves a high return, much higher than stock 3, but not quite as high as stock 1 and stock 2. So it achieves that 18% risk, but does so by achieving minimum return. So anyway, that's it in a nutshell. Again, this follows through the examples in the chapter. I just want to fill in a few details with respect to this. So be sure you do the rest of the prep for the class, and good luck on the prep exam or the prep quiz, and then we'll see you on class on Thursday. Thanks, everybody.